Okay, now it so happens that the three-dimensional problems of elasticity, though easy to formulate, are hard to solve. So the way to get around is to be able to make certain approximations and convert our three-dimensional systems to two-dimensional systems. Okay. One of the things which you should note when we do go ahead with this is that no solid in this universe is two-dimensional, and hence everything which we are doing over here in this particular discussion is an approximation. We learn a certain couple of famous kinds of approximation. Most famous are plane strain and plane stress. You may have already heard of it by this stage. And then we'll see what the exact assumptions are. Okay, why is it an approximate theory, and under what conditions can each of these approximations be used. Okay, so let's take up plane strain to start with. Suppose you have a solid like this. Okay, and then you have a system X, Y, Z. So one of the things about this solid is that it's an infinitely long cylinder. Obviously that infinitely long part is in the Z direction. Now if body forces and tractions on lateral boundaries are independent of the Z coordinate and of the Z coordinate and have no Z component. Then you can write the deformation field within the solid as u is equal to ux comma y, v is equal to vx comma y, and w is equal to 0. So this is the so-called starting point of the plane strain approximation, that if forces and tractions on the lateral boundaries are independent of the Z coordinate and have no Z component, then the displacements can be written only as a function of x for u and v, and for the displacement in the Z direction it is considered to be 0. The logic is that since it's infinitely long in the Z direction, there would be no displacements anywhere in the solid in this direction. Okay, because it's always in comparison with what the length is in the Z direction, and that's infinite. So that way this is the approximation part of it. Okay, so this is obviously plane strain in the XY plane. You can clearly see what the XY plane would be over here. Okay. So the region R is already shown, and then you have from the XYZ coordinate system you have been reduced to a XY two-dimensional coordinate system. Now let's write the strain displacement relations which we had derived earlier. Okay, that would be dou u by dou x, v equal to dou v by dou y. Okay, assuming there is no z component and it's independent of the z, so you will not see a z anywhere. I will just show this to you that how will this happen. So if you look at, say, point restraint displacement relations, for example, if you look at the strain displacement relation EYZ, it should have been half of dou V by dou Z plus dou W by dou Y. Now V is a function of only x and y, and so if you partially differentiate it would be 0. W is a function of, W is actually 0, so when you partially differentiate it you will get a 0 and hence you get a 0. Okay, similarly Ez would be, for example, dou W by dou Z, and this would be 0 because W is 0. Okay, and the rest of the things will remain as they are, and you can find out the other zero strains similarly. So that's the reason we are able to write the strain field in this problem. Okay, so do remember that this is happening because this is an approximation which you have taken because this cylinder was infinitely long, infinitely thick. Okay, and that's how you have taken this. So it's long because you are taking the length along the z direction. So that's how we are able to write it. Now we want to use the Hooke's law to write what the values of stress would be in such a situation. So we want to use the isotropic form of Hooke's law for us to be able to write sigma x is equal to lambda ex plus ey plus 2 mu ex, sigma y is equal to lambda ex plus ey plus 2 mu ey, sigma z is equal to mu of sigma x plus sigma y tau xy. Okay, now we'll see how this can be derived. One of the things is this is also a question from your text. Prove the above. That for an isotropic Hooke's law, this is what will happen. Okay. So let's see. I think this should not be very hard to do. If you pull out the Hooke's law, which we had derived in the discussion on linear elasticity, you would find that, I'll use the green color, you'll find that sigma x is equal to lambda ex plus ey plus ez plus 2 mu ex. Okay, now if you look at this, ex is there, ey is also there, okay, but ez is 0. Ez is 0, so this quantity would become 0, and that would mean that this is equal to lambda ex plus ey plus 2 mu ex. Similarly, take up tau xy. Tau xy is equal to 2 mu exy, and since exy is not equal to 0, we'll just write it as it is. Now take up tau xz, that is equal to 2 mu eyz. Look at what eyz is. Eyz is equal to 0. So this would be equal to 0. And similarly, you can write the other quantities. Okay. And this relation can be written just by using the relationship between lambda and nu. Okay. Now, one of the things which one should note is this expression. This means, I'm putting a star, if sigma x and sigma y are determined, then sigma z can be found. Okay, so you find the first two normal stress components, and along the thickness, along the length, you will be able to find sigma z. Here is another thing to take. See, Ez is 0, but sigma z will not be equal to 0 generally. Okay. One of the things is this, quite important, because it somehow it escapes our intuition, and this has happened again because of the way we have taken the first approximation. This is the only approximation for plane strain, as you see. Anything after this is basically just using the strain displacement relation as it is, and then using the Hooke's law as it is. Okay. So these are the two observations which one has made, and one of the things which you should also note is that all the stress and strain components will be functions of in-plane coordinates, which is x and y only. Reason is the displacements are a function of x and y only, hence the strains will be a function of x and y only, or it will at worst be 0, and because of that the stress will also be a function of x and y only. So this is an important point to note. We will see the importance of this note later on. All strain and stress components will be functions of in-plane coordinates x and y. Okay, so once we have found this, let's now also write the equilibrium equation. That can be written as dou sigma x by dou x plus dou tau xy by dou y plus fx is equal to 0. Dou tau xy by dou x plus dou sigma y by dou y plus fy. So the body forces are not 0, they were only 0 along the lateral surfaces. That's something which you should make a note over here. Now let's see how this could have been done. There are only 3 equilibrium equations. Let's write one of them and see if we can derive one. The other 2 you should be able to derive. Okay, so let's see. dou sigma x by dou x plus dou tau yx by dou y plus dou tau zx by dou z plus fx is equal to so dou sigma x by dou x will remain as it is because sigma x clearly is having this value over here. Dou tau xy or tau yx will have this value which is non-zero, so that remains. Dou tau zx by dou z will be equal to 0 because dou tau zx or dou tau xz is actually 0. So since this quantity is equal to 0, this term will vanish and hence you are coming to this expression. Similarly, you can do the other one, meaning this one. I'm writing the one which is actually missing. Let's see why is it missing. The third equilibrium equation, dou tau xz by dou x plus dou tau yz by dou y plus dou sigma z by dou z plus fz. Okay. So why is this equation missing at all? Let's see. Dou tau xz as you see is 0. Dou tau yz is also 0. Okay, and sigma z is not actually 0, but it is a function of x and y only. So this quantity is 0, this quantity is 0, this quantity is a function of x and y only, and hence once you partially differentiate it with respect to z, you will get a 0. Okay, and then the last part is this, that the body forces along this direction are 0, so that is equal to 0. So that's why the third equilibrium equation is not even being written anywhere in plane strain. So this, it is called, it vanishes identically. Okay, it is 0 by its value. Okay, now one can use the strain displacement relation over here. Sorry, this one, and one can use the Hooke's law, which is this one, and then find out the equilibrium. We want to write the equilibrium. So every time Hooke's law is written in terms of the strain displacement, what you have is the so-called Navier's equation. So we want to do exactly that. Okay, and let's see. So this is again a question from the book, and also the Pentrami-Mitchell compatibility equation. So we'll derive both of them now. Okay, let's see. You start with the Hooke's law, which is sigma x is equal to lambda dou u by dou x plus dou v by dou y plus dou mu dou u by dou x. Okay, sorry, no sigma z obviously in this case, and that would be tau xy is equal to mu dou u by dou y plus dou v by dou x. Okay, now this Hooke's law we want to substitute in the so-called equilibrium equations, these ones. What are the equilibrium equations? So let's just substitute it directly since we can see all of it. So dou sigma x has to go in, so dou by dou x of lambda dou u by dou x plus dou v by dou y plus dou v by, sorry, 2 times of 2 mu dou u by dou x, okay, plus dou by dou y, mu is dou u by dou y plus dou v by dou x plus fx is equal to 0. Okay, so I'm just trying to derive the first Navier equation. I'm sure the other can be done similarly. So let's see. So I've just substituted this and this and this inside this equilibrium equation. Okay, so this eventually gives you mu of, let me just write out, lambda of sorry, this implies that lambda of dou 2 u by dou x square plus dou 2v by dou by dou x. Okay, so let's take a few terms together. Okay, let's take up mu of dou x square okay plus dou 2u by dou y square. Okay, and then you would have a lambda plus mu, which you can take up dou by dou x into okay. So basically this has been split up into two separate terms, and similarly you will have the other Navier's equation. So I'll just write both of them, mu into Laplacian u plus lambda plus mu dou by dou x. Okay, And as you know, Laplacian is a operator. Okay, so this is how the Navier's equation can be derived. Now similarly, you will have a Beltrami-Mitchell compatibility equation. That can be written in the case of plane strain as the first step is obviously the idea is that you have a compatibility equation. Let's say this one. This is the only one which is in terms of x and y only. Okay, that's why we are taking this up. If you have this question that why are we taking this one and why not the other compatibility equations, the reason is that it has all things, it has all the terms which are actually not zero in our approximation. Okay, now to be able to use this, you have to put the Hooke's law into this equation, and for that you will have to actually go and invert the Hooke's law. Okay, so for that there is another question in your text which tells you to basically express the Hooke's law. This is the Hooke's law over here. Okay, you want to express this in the invert way, in the sense the strain is one first. So you want to write it as Ex equal to 1 plus nu by E, and then 1 minus nu sigma x minus nu sigma y. Okay, and similarly you would have E y is equal to 1 plus nu by E, 1 minus nu sigma y minus nu sigma x, and then Exy Okay, so let's start with this. We had already written sigma, let me use another color. We had already written sigma x was equal to lambda of Ex plus I plus 2 mu Ex. Sigma y is equal to lambda of Ex plus Ey plus 2 mu Ey. Sigma x plus sigma y is equal to 2 times of lambda plus mu Ex plus Ey. Okay, so we can just like add and subtract these two, and that should give us this. Now if you solve this and this for Ex and Ey, one should get 2 times of Ex is equal to, let me just write it as Ex is equal to 1 by 2 times of lambda plus mu into sigma x plus sigma y plus 1 by 2 mu sigma x minus sigma y. Okay, one can also write this in the not in lambda and mu but in nu and e, that would make it 1 plus nu by e, 1 minus 2 nu sigma x plus sigma y. Sigma x minus sigma y. Okay, so that's how ex can be derived, and similarly ey and exy. So I'm not writing that out separately, should be easy to do, but do verify this, actually verify this one. Now what we want to do is we want to substitute this strain components into the compatibility equation, and let's see what should that give us. So dou 2 by dou y square of ex is what? 1 plus nu by e, 1 minus nu sigma x minus nu sigma y. One plus nu by e, 1 minus nu by sigma y minus nu sigma x. Okay, and then what's the, this is equal to 2 times of dou x dou y of exy. So exy is simple, 1 plus nu by e tau xy. Okay, now let's see if we can simplify it in any way. So 1 plus nu by e is common everywhere, and since this quantity is not equal to 0, we can divide both sides by 1 plus nu by e. Okay, so that would imply that 1 minus nu dou 2 sigma x by dou y square minus nu into dou 2 sigma y by dou y square plus 1 minus nu dou 2 sigma y by dou x square minus nu dou 2 sigma x by dou x. Sorry, this should be written as 2 times of dou 2 by dou x dou y tau xy. Okay. Okay. Dou 2 by dou y square plus dou 2 by dou x square of, this operator is applied on sigma x. This is equal to 2 times of dou 2 tau xy by dou x dou y plus nu. Now so let me just write it out separately. I think dou 2 sigma x dou y square plus dou 2 sigma y dou x square minus nu dou 2 sigma x whole to minus So where is the body force? Somehow okay, so this should give you 1 minus nu when you have the equilibrium equation dou sigma x by dou x plus dou tau xy by dou y plus fx. This should imply you have a minus of dou f equal to dou 2 sigma x by dou x square plus dou x dou y. Similarly, you should write the other equilibrium equation, and then you should have minus dou y equal to dou 2 sigma y by dou y square plus dou 2 tau xy dou y dou x. Okay, now you can see that this quantity can be written in terms of actually this quantity entirely can be written as equal to minus of dou fx by dou x plus dou fy by dou y. Okay, once this is done, one can write 1 minus nu okay, 1 minus okay, sigma x plus sigma y is equal to minus of dou fx by dou x plus dou fy by dou y. This would mean that the Laplacian of Okay, so this is your Pentrami-Mitchell compatibility equation, and what you can see is that we have the plane strain problem is formulated in the two-dimensional region R. There's a boundary. Okay, so this 3D has been converted to a 2D, and this is the region R, X and Y. Now the displacement formulation for this case, so let's write the boundary conditions. Okay, the formulation is never complete unless you write the boundary conditions. So we started with the displacements, then we wrote the strains, we wrote the stresses, then we wrote the equilibrium equations, then we wrote the Navier's equation, then we wrote the compatibility equation, and then the Beltrami-Mitchell compatibility equation, which is the compatibility equation in terms of stress. Just like the Navier equation is the equilibrium equation in terms of displacements. And the final part is to include the boundary condition. So the displacement formulation, okay, you don't remember the elasticity problems can be formulated in two ways, one using displacement, the other using tractions. So this is the first part, which is the displacement formulation. You would formulate your problem in terms of displacements if the boundary conditions are primarily in terms of displacement. So u would be equal to ub x comma y, v will be equal to vb x comma y on S. Okay, and then the stress, if you would want to write using the tractions, one would say that Txn is equal to, using the on the boundary x comma y, it is equal to sigma x on S is important, okay, on the boundary. So what would be the formulation of the plane strain approximation? To find u, v, ex, ey, exy, sigma x, sigma y, tau xy in R, the interior region R, given that the boundary conditions are given and the material properties are also given. Okay, you please see that we have not said to find sigma z, even though that quantity is not zero. The reason is, once you know sigma x and y, you can find sigma z. So we don't write it in the problem formulation for plane strain. Yes, it's an unknown, but it can be found. So this completes the formulation of a plane strain problem. Okay, now you will obviously living in a world in which the certain assumptions which we had taken at the start of this would not actually be true. Let's see what those two things are. First, body is of finite length along z-axis. Okay. You are unlikely to find structures or solids which are of infinite thickness. So we want to see how this changes when we have a realistic situation. I mean, consider an experiment which you have to do in a lab. It will always have a finite thickness. Okay. So let's consider that case first. So you have your boundary now, which is at z is equal to plus minus L. Okay. It is fixed. The boundaries are fixed and frictionless. This is an assumption which we have taken now. Okay, it's a finite length which are fixed and frictionless. What does this tell us about the displacements? It tells us that at the displacement in the z direction, which is w, is x comma y plus minus L, is actually equal to 0. Okay, because it's fixed, and tau xz, x comma y plus minus L, is equal to tau yz, x comma y plus minus L, is equal to 0 because it is frictionless. So it is fixed and it is frictionless. Please think very carefully about these two situations. Okay. Now, this is the thing. If you now redo your problem, okay, redo, what would you redo? You would find strain using the strain displacement. You would find the stress, okay. You would find the equilibrium equation. You would find the Navier's equation or the Pentrami-Mitchell equation and so on. Okay, compatibility equation. They will all be the exact same which you have done. The reason is w equal to 0, tau xz is equal to 0, and tau yz is equal to 0 is something which you have already done. See, w is equal to 0, okay. Tau xz and tau yz is also equal to 0. So these conditions will be identically satisfied by the original plane strain formulation, okay, and hence this implies that the original plane strain formulation satisfies the finite length problem. Okay, so think about this very carefully. What I want you to think about is, I mean, this seems to be valid at the boundary. What happens to the bulk? Okay, and because in the earlier case when you had said that these quantities are 0, you meant it through, and this is only there, but then how can it be true everywhere? Again, you have to now think that it's actually a two-dimensional approximation, so there's no thickness anywhere anyways. So those are the lines which you should think and sort of confirm that you have understood what we have just discussed. Okay, now the restraining forces in this case at ends, okay, to keep it. What are the restraining forces? To keep it fixed. So to keep anything fixed, you need restraining forces. Okay, restraining forces, and clearly it's frictionless, so the shear parts will be 0. That's, you have already taken 0. So to calculate the restraining forces, what you have to do is you have to just take sigma z and integrate over the whole region R. Okay, so this is your R. Take a sigma z and just integrate it over. Now how to we solve or use this in a realistic case where friction is present. Okay, what you will do is you will use the same with Saint Venant's principle. Okay, so clearly the boundary condition will be different, but the solution far away from the boundary points will approximately be the same. So that's how you can use this formulation even in a case where friction is present. Okay, so let's take up one more case. And actually a question from the text. The plane strain to a cylindrical body of finite length with zero end tractions can be found by adding corrective solution to remove the unwanted and loadings being generated by this term. Okay, so if there is absolutely zero end tractions, okay, how would you then solve this problem? Because you have to actually eliminate this part, that sigma z it will generate because of the sigma x plus sigma y. What we have to do is, like, using Saint Venant's principle, show that the corrective approximation this correction should be equal to ax plus by plus c. A, B, C are constants. We want to know how can this be found using principal centroidal xy axis. Show Okay, let's see how we can do this. The eventual objective is that it should become a traction. The traction should disappear. So obviously the total strain in the z direction should be equal to sigma z plus sigma z correction. So this is the actual one, this is the correction. Okay, and the actual sigma z, as you know, is nu into sigma x plus sigma y, and sigma z has this corrective form of ax plus by plus c is equal to 0. Now we want to say that Rz, which is this integration over this area, let's call this a hat, is sigma z total. Okay, dA is equal to 0. So there should be no resultant force as such, and that would mean that a hat into sigma z plus sigma zc dA hat is equal to 0. This implies a hat sigma z dA hat is equal to minus a hat ax plus by plus c dA dash is equal to minus ca hat for principal axis. Can you think of a reason why? Why should these two integrals disappear, ax and by ones? Then c can be found out as 1 minus by a hat sigma z dA hat. Similarly, if you do your mx, the moment along the x direction, that would be a hat into sigma z of t into y dA hat, and that must be equal to 0. And you will do similar substitutions and find out that b would come out to be minus 1 by ix into a hat sigma z y dA hat. So please verify this. Do not ignore this. Do not proceed ahead without actually verifying all these two things. Okay, so that's where we are for the plane strain part. Now let's try and see what we can do about plane stress. What is it? Okay, so we want to apply this to a domain bounded by separated by a distance that is small compared to the other dimensions in the problem. Okay, so let's take up something like this, and then another. Okay, and clearly this distance is, sorry, not z, this distance of, should draw a nicer figure. So we have a domain which is bounded by two parallel planes. Then you can say that your x direction is like this, y is like this, and z is like this. Okay, and clearly this 2h is very small compared to other dimensions. Your domain is R. Okay, now let's see what it has with us. So the planes are obviously z is equal to plus minus h, parallel planes. So there is a further assumption, just like the assumption was that u and v will be a function of x, y, and w will be 0 in the previous case. The assumption over here is that these planes z equal to plus minus h are stress free. That would mean that sigma z is equal to tau x z is equal to tau y z is equal to 0 on each face. Each face is equal to z equal to plus minus h. Now this is the cornerstone of this theory, because the region is thin. Let me explain what I mean. See, this region is very thin over here. So if the stress, say sigma z is 0 on this face and it is 0 on this face, okay, these two faces it is very 0, it is highly unlikely, say you have z is equal to minus h and z equal to plus h, and say this axis is sigma z. So if this is 0 over here and this is 0 over here, it's true. Now this distance of 2h or h is so small that it is highly unlikely that it will rise from 0 to a considerable value and then come back to 0. Okay, just because this distance is too small to allow this variation. What will usually happen, that very likely it will be, maybe at worst it will be something like this, maybe something like this. Okay, so this is what is the reason that sigma z and tau xz and tau yz is taken as 0 throughout, because it is highly unlikely that it will start from 0, go to some considerable value, and which is not 0, and then come back to 0. So it is approximated to be 0 throughout the domain. It is also an approximation, and it comes from the fact that you have a very thin specimen. Okay, the boundaries are very thin. Okay, now if you want to summarize this, what do we have? You have the region is also, the region is, so this is the second part of it. Moreover, the region is thin in z direction. Therefore, it can be argued that the stress components will not have any variation with respect to z. Same reason, right? I mean, sigma x can vary definitely, okay, but it will not vary in the z direction just because the distance is too small. It can vary across the region R in x and y, but not along z. So that gives us that sigma x should be a function of xy only, sigma y should be a function of xy only, tau xy will be tau xy x comma y, and sigma z is equal to tau xz is equal to tau yz equal to 0. Okay, so once this is taken care of, let's just try to write. So this is a state of plane stress. You have clearly seen under what domain we are applying this approximation. You have clearly seen why we are writing the stresses as they are in this one. So you also want to maintain a stress field which is independent of z. Okay, so that automatically implies that you cannot have an fz. Okay, because if there is, then due to the equilibrium equations, you will start having stress field which is dependent on the z. Okay, so you cannot have a body force or a surface traction in the z direction. Sorry, it is equal to 0. Okay. Okay, now you want to use the Hooke's law again, this time just the inverse one. So let's write out Ex is equal to 1 by E sigma x minus nu sigma y. Ey is equal to 1 by E sigma y minus nu of sigma x. Ez is equal to minus nu by E sigma x plus sigma y equal to minus nu by 1 minus nu Ex plus Ey, and then Exy is equal to 1 plus nu by E tau xy, and Exz and Eyz is equal to 0. Okay, so how has this happened? Very easy. I mean, just look up the inverse Hooke's law, which we had derived in the discussion on linear elasticity, and it should be easy for us to sort of write this. So let's write a couple of them. So Ex in the linear elasticity was 1 by E sigma x minus okay, and this particular quantity is 0. Okay, and for the reasons which we have seen, so then you will get this term, and similarly the other terms are also easily found out. Okay, just using this inverse Hooke's law. So like we had done before, you can write out Ez as you see in terms of Ex and Ey. Okay, so if you find Ex and Ey at any point, you can just find Ez, so you don't have to separately go out and find it. One of the things which you will notice again, that although Ez is equal to 0 for plane strain, remember it was 0 over there, it will not vanish generally, okay, for plane stress. For plane strain it was always equal to 0. For plane stress very likely it will not be 0 in the most general case. So obviously all the strains over here will be function of x, y only, okay, not z. Just because sigma x, sigma y and tau xy are not functions of z, so it is impossible for you to have strains which are functions of z. Okay, you can also do an inversion. You can also invert this and find out, say, what sigma x would be and sigma y would be and so on, tau xy. Okay, please do this. This is also a question from your text, so I can write out the expressions so that you can verify that you have done this correctly. And tau xy is equal to okay. So once the stress is found in terms of strain or the strains is found in terms of stress, you can now invoke the reason we had to go this way is because we started off with stresses this time, okay, unlike the plane strain where we started off with displacements. So after the stresses have been found in terms of strains, we can write out this as say the strain displacement relations can now be invoked. So Ex would be equal to dou u by dou x, Ey would be equal to dou v by dou y, and Ez will be equal to dou w by dou z. Exy dou u by dou y will be equal to half of xz is equal to half into dou u by dou z dou w by dou x. So this clearly we would want to be equal to 0. Why is this equal to 0, these two things? Because okay, exz and eyz would be equal to 0 once you use the Hooke's law. Okay, so that's why, and this would clearly be 0 because the corresponding shear stresses are 0. So you have done this. Now if you look at this and this and this, it gives you some unwanted results, and this is also say a question of your text. So A, B and C gives some unwanted results. Let's see what they are. If you look at A, it is Ez is equal to dou W by dou Z. This clearly implies that W is a function Ez Z plus some function of x and y. If you do an indefinite integration, you will find that it's an arbitrary function x and y. Okay, and you can always check, you can differentiate this with respect to z partially and you would get Ez. Okay, now if you look at this expression over here, so where did it go? This one, Ez is equal to minus nu by 1 minus nu and ex plus ey. Okay, let's see this as Ez is equal to minus nu 1 minus nu ex plus ey. This implies that Ez is also a function of x and y. Okay, the reason this will happen is because if ex is a function of x and y, ey is a function of x and y, so ex plus ey will also be a function of x and y, and that is Ez. Okay, that's why we say that Ez is also a function of x and y. Now eyz is and the word also is definitely important. Now eyz is clearly half of dou v by dou z plus dou w by dou z is equal to 0. This would imply that dou v by dou z is equal to minus of dw by dz. Okay, but w is this, so we can write it as minus of dou e z by dou y z. Sorry, this is dou w by dou y. Okay, and that should be equal to dou f. Okay, this implies that v is equal to minus of half of dou Ez by dou y into z square minus dou f by dou y into z plus some other arbitrary function of x and y when you do an indefinite integration. Okay, similarly exz is equal to half of dou u by dou z plus dou w by dou x equal to 0. This would mean that dou u by dou z is equal to minus of dou w by dou x. This is equal to, this implies that u will be equal to minus of half dou e z dou x z square minus dou f by dou x z plus h of x comma y. So clearly just g and h are arbitrary functions of x and y, and they have come up because of this indefinite integration which we have just done. Now carefully look at this and this. U and v depend on z, right? You have a z over here, you have a z over here, you have a z over here, you have a z over here. So clearly u and v depend on z. So this means, and see, until this point it has not violated any theory, because you never assumed that u and v were a function of x and y. In this theory you just assumed that the stresses were a function of x and y. So there is nothing mathematically wrong with what you have done until now. Okay, but you have found that u and v are actually depend on z. So this implies that plane stress is actually three-dimensional theory. Okay, so plane stress is a weaker approximation, definitely. The reason is it produces these three-dimensional displacement. So the whole point was to keep it two-dimensional, and now if you're getting displacements which are three-dimensional, that causes a lot of problems for us because it doesn't really help much. This was a point of discussion just to sort of discuss the drawback of plane stress and why it's happening, and you should be aware of it. In practice, when we say, when we do experiments, when we do simulation, we ignore this. We just assume that this u and v will only depend on x and y and not z. This is how it has been happening until now, and I just thought you as a student should know about it, that you ignore the fact that u and v are actually functions of z in practice. Okay, so once this is sort of out, then it is very easy for us to write the equilibrium equations just like the previous case. Okay, and fz clearly is 0, and fx and fy will be functions of x and y only. Again, when the equilibrium equations are written in terms of displacement, you get the Navier's equation, and that is u and v, sorry. Okay, so this is somewhat which you should verify. Please don't leave this, verify and only then move ahead. Okay, one thing which can be noticed over here, that these relations which you have developed for plane stress are identical, are somewhat similar to that which you developed for plane strain. So look at this one. This is for Navier's equation for plane stress, and for plane strain, if you go, okay, so there is difference of some constants, but it looks similar in form. Okay, and that's something which you should note, and that's something which we'll be using very often to convert from plane strain or plane stress depending on what the situation is. Okay, now obviously we want to have the compatibility equation, but as you know that Ez has to be ignored. Okay, so this brings out the approximate nature of the plane stress formulation. So you have the 6 compatibility equations. Okay, neglect the ones which have Ez. Okay, and that's clearly an approximate nature of this theory. Why is it an approximate nature? Because all the compatibility equations must be satisfied. Okay, not just one of them. So that is a nature of this. So let's see one case. If we are let's take up one question from this text. So dou 2 Ez by dou x square is equal to 0. Dou 2 Ez by dou y square is equal to 0, and dou 2 Ez dou x by dou y is equal to 0. We want to first integrate, now then integrate them to say that Ez will be equal to ax plus by plus c, and then the question is that in light of the fact that Ez is equal to minus nu 1 minus nu ex plus ey, will this result be generally satisfied? Okay, so if you just look out the equations which you are ignoring because Ez term, they are dou 2, you should have the 6 compatibility equations in front of you. Dou z square this implies that dou 2 Ez dou y square is equal to 0. Okay, the reason is quite simple. I mean, this is not a function of z, okay, and similarly this is not a function of z, so the only thing which you are left out with is the middle term. And similarly you can use the other compatibility equation. Let's see, dou 2 ex by dou x square plus dou 2 ex 2z square. Is this the one? Let me check. So there's a 2, I think. Okay, so there's a 2 over here, and that is 2e zx, do z to x, z, this is a z. Okay, so this implies that dou 2ex by dou x square, sorry, z square is equal to 0. Reason is that ex is a function of x and y, so once you partially differentiate with respect to z, you get a 0. Ezx is also a function of x and y, or I think it's actually 0. So that is the reason that this will be 0, and you will be only left out with this. And similarly, you have to know which equation should give you okay. Now these are the three things which you have sort of shown for the neglected compatibility equations. Now if you integrate each one of them, okay, integrate each one of them, let's take up one by one at a time. So dou 2ez by dou x square is equal to 0. This implies dou ez by and then dou 2ez by dou y square is equal to 0. This implies dou ez by dou y is equal to g of x. Okay, this is a indefinite integration term. And then dou 2ex by dou 2ez, sorry, dou x dou y is equal to 0. This implies that f dash of y is equal to g dash of x is equal to 0. Okay. From this and this, I think you can easily say this, and you should know what that differentiation, what that dash is in terms of which differentiation does it make. Now once this is true, this implies that f of y is actually a constant. If the derivative of something is equal to 0, then it's a constant. Similarly, g of x is also a constant, and it's equal to b. Now you can write dou ez by dou x is equal to f of y is equal to a. This implies ez is equal to ax plus f of y. Okay, and this would mean that g of x, okay, so we have written this capital F as a function of y, and the same has to be taken over here. So this should give you f dash of y is equal to p. This implies that fy is equal to by plus c. Obviously c is an arbitrary constant everywhere, and that would mean that ez is equal to ax plus by plus c. You can look at all these three things. This gives you this. So this also proves what was required, that ez is of this form. Now the question is that since ez is equal to ex plus ey, will this result be generally satisfied? So the question, so you should think of an answer. Okay, along the lines of is Ez linear? Okay, and if it's not, then what happens? If it is, then what happens? Okay, so this is a good thing to be done at this time. So coming back, the only compatibility equation which is left out for us is okay, and this should give the Pentrami-Michel equation. Since I have done this for plane strain, I expect it will be done by you for plane stress. Okay, please don't proceed ahead without actually doing this. Okay, so we have now formulated our two-dimensional region R, and the problem can be formulated for a plane stress approximation. Clearly the unknowns are u, v, ex, ey, exy, sigma x, sigma y, and tau xy in R. This is the unknown, and obviously Ez is not separately written because it can be found out by finding Ex and Ey. That completes the formulation. Now, as you had seen, that all the expressions which we are getting are actually very similar to that of plane strain. So there is a very simple conversion to be done for these equations. I mean, if you have equations for one, you can write. So if you want to convert plane stress to plane strain, just replace E by E into 1 minus nu square and nu by nu minus 1 minus nu, or plane strain to plane stress, you can write as a E by 1 plus 2 nu 1 plus nu whole square nu by 1 plus nu. Okay, obviously if nu is equal to 0, when does this happen? That's also something you should know. The plane strain and plane stress approximations are having same expressions. Okay. So we have just seen that the plane stress is not actually two-dimensional approximation because it has these characteristics of a three-dimensional theory, and hence it's somewhat of a weaker theory compared to plane strain. So that inconsistency we had noticed. Now what we want to do is, I mean, one way was to just like ignore the inconsistencies and go ahead, which, as I have said, works. But if you want to sort of theoretically rectify that, then this concept of generalized plane stress has been developed. Okay, so we'll be discussing that. What is generalized plane stress? So what it does is it sort of works on averaging the field quantities through the thickness. Okay, very simply, remember there were components of which were dependent on z component. Okay, so like there were displacements and things like that which were dependent on z, which was inconsistent. So how do you remove that dependence on z? Do something like this. If you have a quantity which depends on x, y and z, okay, just integrate it over the entire thickness, and then you will have a quantity which is only dependent on x and y. So this is the easiest way to get around this problem, and this is called generalized plane stress. Okay, so doing this operation will remove any dependency on the z coordinate. So that assumption that h is smaller, much smaller than the other dimensions with this problem is still holding. So you can't like remove that, otherwise it's not plane stress. Okay. So if you have the tractions on the faces are again taken 0 on surfaces z equal to plus minus h, and the loadings on the edges of the plate have no z components and either are independent of z or are symmetrically distributed through the thickness. The concept is there is no z occurring anywhere in the boundary condition. So doing this, you are able to ensure that z is not dependent, z is not occurring in the internal part of the, say, displacement, strain, stresses and everywhere. But for the boundary, what do? You want the same to be happening at the boundary as well. No z dependence at all. So first thing, the tractions on the surface z is equal to plus minus s are again taken to be 0. Then how do you deal with the other things? So the loadings on the edges have no z component and are either independent of z symmetrically distributed. Thickness, because if they are symmetrically distributed, then you can just assume that essentially they are 0. Okay, or I mean in an average sense they will integrate, they will become 0. Okay, so in these assumptions, the out of plane displacement, remember u and v are the in plane displacement, the out of plane displacement will be minus w x y, sorry, x comma y comma minus z, the so-called odd function. You must have heard of an odd function and an even function. So the middle points will clearly have no displacement. Okay, this implies that wx comma y comma 0 is equal to 0, and that would mean that if you do this averaging, which I had just mentioned over here, okay, you will find minus h to h w of x comma y comma z dz is equal to 0. Okay, okay, now at this these two surfaces sigma z and x comma y plus minus h is the same as okay, so these are the assumed stress. If you know the stress, you know the tractions as well. Okay. Now the equilibrium equation in the z direction similarly will become dou tau xz by dou x plus dou tau yz by dou y plus dou sigma z dou z is equal to 0. Okay, so this is the equilibrium equation. So you want to apply this at z equal to plus minus h. At z equal to plus minus h, this term will be 0. Okay, and this term would be 0. So what you would be left out is dou sigma z by dou z at x comma y plus minus h is equal to 0. So this implies that at z equal to plus minus h, both sigma z and its normal derivative vanish. Okay, sigma z is definitely vanishing and the derivative is also vanishing. Okay, so you have seen how a Taylor series works. Okay, that if there is a vanishing at z equal to plus h, then a small distance away from it in the interior, the value would be, say, sigma z of z equal to plus h, say minus delta. Okay, and then you can write it in a form in which you will have a sigma z of z equal to plus h plus some sort of a derivative and then the higher order terms. Okay, so since this term and this term would be 0, that means that sigma z of at h minus delta, which is an internal point, not the boundary, is also equal to 0. Okay, so the first two terms in this Taylor series expansion will be 0. One thing which you should do is write the Taylor series expansion. Expansion correctly over here and then convince yourself. So this justifies the assumption that sigma z vanishes throughout the interior of the plate. Thin plate to be mentioned. Okay, now if you just take the average of the remaining fields, okay, then you would find that u bar is equal to u bar x comma y, v bar is equal to v bar x comma y, and w bar is equal to 0. Okay, then sigma z bar is equal to, bars show the averaged value, Okay. By the same logic, sigma z is 0 in the interior, tau xz and tau yz will also be 0 in the interior. Okay, exactly the same logic. Now, then the sigma x bar can be written as this is the Hooke's law. Obviously, the averaged parameters are being used now. So lambda star over here would be 2 lambda mu by lambda plus 2 mu. Okay, you should verify all these expressions. Then the equilibrium equations, again the other two equilibrium equations would become, now in the average sense, that would become dou sigma x bar by dou x plus dou tau xy bar by dou y plus fx bar is equal to 0. Do remember that if you are writing any equation, we're using the averaged parameter, averaged term. All the terms in that should be averaged. You cannot write half of it in, for example, fy bar has to occur over here. Okay, and when the equilibrium equation are written in terms of displacement, that would be called the compatibility equation. Okay, so in terms of okay, this would be written as mu Laplacian. Okay, so this lambda star plus mu is equal to e by 2 into 1 minus nu. Again, the compatibility equation in terms of the stresses, Beltrami-Mitchell compatibility equation would come out to be so the coefficients again here would be mu of lambda square plus 2 mu 1 plus nu. What you would notice is that verify that the above relations in terms of averaged values are the same as the original plane stress. Obviously, the advantage is that all the equations are exactly satisfied by these values. Okay, there is no inconsistency anywhere with having a z dependence. The reason was we had so-called killed the z dependence here itself. Okay, and once you do that here itself, it will not occur anywhere else. So this is the reason that this formulation will exactly satisfy all the averaged variables of displacement, strain, stresses, and so on. Okay, but it does happen that applying this theory, generalized plane stress, is rigorous. Okay, you can see how averaging is needed everywhere. Okay, what we do is we just because of this rigor we just ignore this theory as such and continue using the the plane stress which we had learned before, just because first reason this the equations are exactly the same, so this rigor is not worth it. Okay, though it still has its problem, but we just continue to use it. So in a practical sense, that's what happens. Okay, another theory which should be sort of mentioned over here is called antiplane strain. So we have read about the plane strain, and an additional theory is the antiplane strain. What is it about? It involves the formulation based on the existence of only out of plane deformation. Okay, so you may have a plane strain, you have a situation in which only the out of plane deformation exists and the other terms are zero. This is normally used in, say, geomechanics, okay, where the specimens are extremely buried some deep inside the earth or like a rock, and then the deformation is best defined out of the plane because the inside of the plane is in plane ones are constrained. So in plane components of displacement are zero, out of plane clearly exists. Okay, the strain field is quite simple in this case. That's equal to half. And then you can write the Hooke's law. Then the stresses would be Now the equilibrium equations, again the body forces, if they are, so the equilibrium equation would only mean, okay, so this body forces in the x and y direction are 0, body force density is 0. It comes out if you put all these stress components in the equilibrium equation, okay. This is not an assumption that the body forces are 0 in the x and y direction. And the third equilibrium equation gives you this, okay. And when the equilibrium equation are written in terms of the displacements only, we find this as our Navier's equation. Okay, so just like many other cases which we have seen, the boundary conditions also can be written that W is equal to WB XY on S, okay, or in the traction form, which would mean that Tz of n is equal to Tz of B x comma y is equal to tau xy and x plus. This is the strain traction, the stress traction relation, and this can be written if you substitute this tau xz from over here and tau yz from over here. You can write it as mu into dou w by dou x nx plus dou w by dou y ny on S. So this is all on the boundary. Okay. So what does the problem, the boundary value problem involve? It involves us finding the unknowns W, EXZ, EYZ, EXZ, sorry, tau XZ. Okay. And then the Airy stress function is our next topic. One of the things which you should do for this is to verify all relations below. Okay, all the equations which I have written, they are actually very simple to do, but you must verify to confirm that you have understood this part. Okay, so let's now discuss this Airy stress function, which is the sort of starting point of us being able to solve boundary value problems. Okay, so you must have learned in the earlier chapters briefly about the methods which exist to solve elasticity problems. Okay, but let's make one start which in detail with us. And what this does is it reduces the formulation of the all these equations, like which any plane strain, plane stress which you follow, it has all these equations. Displacement is assumed, sometimes attraction or stress is assumed, and then the stresses and the equilibrium equation, Navier's equation and compatibility equation. What Airy stress function does, it reduces the formulation into a single governing equation in terms of a single unknown. This is what it does. Okay, it reduces the general formulation a single governing equation in terms of a single unknown, and that unknown is called the stress function. We'll see how that works. Okay. So look at the equilibrium equation of either plane strain or plane stress. Okay, they are actually the same equation, but if you want to write the equilibrium equations, of either plane strain or plane stress. Okay, how do they look like? Please check whether this is correct. Okay. How does this theory work? Assume that the body forces are derivable from a potential function V such that f(x) is equal to minus 2v by 2x and fy is equal to minus 2v by 2y. Okay, now making this assumption is not very restrictive. Most of the forces are actually based on a potential function. For example, consider the force of gravity. If the potential is phi is equal to g m1 m2 by r, the force between them is minus of is d phi by dr. That would make it minus of g m1 m2 by r square, minus sign indicating it's a attractive force and so on. Okay, so to assume that a body force is derivable from a potential function is not restrictive. Like the force of gravity, as we have seen, is an example where the body force is actually derivable from a potential function. So that's there, and hence we have taken this minus sign for our convenience, though plus minus is just a play of sign convention. Now we want to put this and this into the equilibrium equation. This should give us dou of sigma x minus v by 2x plus dou of tau xy by dou y equal to 0, dou tau xy Okay, so just putting this body force density into the equilibrium equation gives us this. Okay, now the statement is that it is observed that these equations, these meaning these two, will be identically satisfied if you take sigma x as dou 2 phi by dou y square plus v, sigma y is equal to dou 2 phi by dou x square plus v, and tau xy is equal to minus dou 2 phi by dou x dou y, where form called Airy's stress function. So let's just see whether this is actually working. We will want to substitute it over here, so I'll just take the first equation, dou by dou x. Sigma x is what? Dou 2 phi by dou y square plus v, okay, minus v, then dou by dou y minus of dou 2 phi by dou x dou y. So this is the left hand side of first equilibrium equation, basically this one. Okay, so I'm taking the left hand side of this. Now I want to write it as dou 3 phi by dou y square dou x plus v and minus v gets cancelled, minus dou 3 phi by dou x dou 2y. Okay, and this is equal to 0 because order of differentiation does not matter. So whether you differentiate it first with respect to y square and then with respect to x, or first with respect and then with y square, I'm sorry, this should be, it should not matter, and this is equal to the RHS, and hence this equation is identically satisfied. You can verify the same for the second equation, meaning this one, and you will get the same. So this is a very powerful idea, that you have now reduced everything to this unknown phi. If you know phi, you know sigma x, sigma y, and tau xy. Once you know this, you can find all the other values as well. Okay, like the strains and stresses, strains and displacements as well, using the Hooke's law and the strain displacement relation. Okay, so the equilibrium equations are satisfied. Now let's take care of the rest of the ones. Okay, so I'll just take up, say, the, let's see which one should we take. We can take up say the compatibility equation. So the equilibrium equations are satisfied. I am not going to the form in which the equilibrium equation is written in terms of displacement, which is the Navier's equation. Let me come to the Beltrami-Mitchell compatibility equation. Okay, and that form comes out to be and dou 4 phi by dou x4. So this is for plane strain. Okay, all you have to do is just go to the Beltrami-Mitchell compatibility equation for plane strain and substitute this. For sigma x substitute this, sigma y substitute this, tau xy substitute this. Similarly, go to the Beltrami-Mitchell compatibility equation for the plane stress, you would find that this turns out to be this is for plane stress. So let's do this. It's a question from the book as well. We want to derive these above two equations. Okay, so as I've said, all you have to do is just substitute the say for plane strain. Let me do that. So for plane strain, the Beltrami-Mitchell compatibility equation is V2 x. Okay, now what you have to do is just substitute sigma x is equal to this term, okay, sigma y and tau xy in this one, okay, and fx is clearly written in terms of v. So this should give you, and you should check this, that so this is the same equation as, sorry, this is the same equation as this one, okay, because this equation can also be written as okay. So for plane strain and plane stress, this similarly can be derived. So let me just write out so this form is called by harmonic operator. Okay, now if there are two possibilities, one is that if this is true, or the body force vanishes, which is fx is equal to 0, fx and fy to 0, okay. First let's take one case, okay, sorry. If this is true, then plane strain or plane stress. Now one of the other statements is there that if body forces is 0, then also it should convert to this form. So let's check that. If fx is equal to fy is equal to 0, this implies dou v by what was fx, was it, yes, minus dou v by dou x. So dou v by dou x is equal to dou v by dou y is equal to 0, and if this is true, then check whether this implies that this is also true. Check. And again, if this is also true, then this is equal to 0 for both plane stress and plane strain. Okay. So just to write this in a lengthier form, this is the biharmonic equation for both plane strain and plane stress. Okay. All we have to do is find phi, because if you find phi using this equation, obviously this phi must satisfy this, and if you have a phi, you will get the stress at any point by substituting phi over here, and then you can get whatever else unknowns you want. Once you have the stress, you can find any other unknown like a strain at the same point and so on. And that's why it's called the Airy stress function, because it helps you find the stress at any interior point in the solid. So to see an application of this, okay, so there are several methods of how this phi can be found out, and this part forms a part of the solution of boundary value problem which has been formulated. Okay, so clearly the phi must satisfy this. Okay, one method which we will see now is the so-called polynomial. Okay, and this is valid obviously for a Cartesian coordinate system, which we have been dealing with now. So what you do is you assume that phi xy is actually a polynomial of this form. Okay, so the objective is again to find phi, and now if you have taken this form, the unknowns are amn, okay, unknown constant. If you somehow know all the amn's, a00, a01, a10, a21 and so on until infinity, then you can find out phi, because x and y are just the variables. And once you have phi, you will just put it in the relationship for stress, and then you will find the value of x and y. So for example, at this particular x comma y, if you have a phi of x comma y, okay, you will also have, say, sigma x, sigma y and tau x, y at the same point. For some other point, there will be a different x comma y and so on. So this phi must be like applied over the whole elastic body. It must satisfy this relation in terms of this polynomial. Okay. So how do you go about solving this? Let's take the stress functions for a zero body force. Okay. So sigma x was equal to d2 phi by dou y square. Sigma y is equal to dou 2 phi by dou x square, and tau x y is equal to minus of dou 2 phi by dou x dou y. Okay, this is for zero body forces. Okay, let's see the contribution of terms which are say phi of xy is equal to a00 x0 y0 plus a01 x0 y1 plus a10 x1 y0 plus other terms. Okay, so m is equal to 1 and n is equal to 1 till infinity. Now if you see the contribution of these three terms, to be specific, okay, what are these three terms? M plus n is smaller than equal to 1. Here m plus n is 0, here m plus n is 1, here m plus n is also 1. Now it is said that they will not contribute to the stress. Why would they not contribute to the stress? Because you see, you have to differentiate. Say sigma x will be equal to, if you differentiate this term with respect to y square, you will get a 0. Okay, you would differentiate the next term, this term, okay, with respect to y square, you will again get a 0, and you differentiate this term, you will again get a 0. Similarly, for sigma y and tau xy also, the first three terms will not contribute to the stresses. You will have no component of stresses. Please verify this. Okay, no contribution to stress, because it requires a two-time derivative, and because there is no parameter which is to the raised to the power of 2, it will always be 0 to stress. So what do they do? We drop three terms. Okay, you can also see that the second order terms, in the sense a20, okay, what would it be? A11 and a02, which is x0 y2, okay, they will produce a constant stress field. Okay, second order, let's see, sigma x is equal to, okay, so there are higher order terms, I'm just showing by high. This is phi x comma y, higher order terms. Okay, polynomial I'm not writing. Okay, higher than basically 2. So yeah, so m plus n basically is m plus n greater than 3 or greater than 2, to be specific. Okay, not equal to but greater than 2. Okay, so let's see, sigma x would be equal to dou 2 phi by dou y square. This term is 0, this term is 0, and this term would give you a02. Okay, sigma y would be dou 2 phi by dou x square, so a20 plus 0 plus 0, and tau xy will be equal to minus of d2 phi by dx, so that would be 2 times of minus of d2 phi by dou x dou y. So this term, first term, would give you a 0 because there is no y there. The second term will give you this minus of a11, plus this would give you again a 0 because there is no x. Okay, so in all these three situations, the stress, the second order terms will give a constant stress field. Okay, and similarly the third order will give you a linear stress field, linear distribution of stress. So please verify this. Okay, now for m plus n smaller than equal to 3, this satisfies this equation, biharmonic equation, for any choice of constants a, m, n. Okay, so if you put any AMN, like what are the options? A00, A30, A21, A12, obviously, A03, okay, and even A11 and what are the others? 3, 1 cannot be. Okay, so it seems, yeah, so terms like this, if you have, they will all satisfy the biharmonic equation. Okay, check this. All you have to do is take up a few of these terms as phi, and then just see whether the biharmonic equation are satisfied. Okay, now for higher order terms, meaning m plus n greater than 3, the constants must be related to satisfy biharmonic equation, meaning they are not independent of each other. Let's take an example. Let's take a phi xy which looks like this. Okay, this is clearly a case where m plus n is greater than 4. So there are other possibilities as well, but we are just taking one example. Okay, now if you substitute this into the biharmonic equation, let's see what we should get. We should first write the biharmonic equation. Okay, so so this would be 2 4 a40 x to the power of 4 plus a22 x square y square plus a04. So let's try to write directly. Okay, so this would give you x to the power of 4 would be a40. Take the LHS of this. Okay, we don't assume that it's already satisfied, so take the LHS of this. To the power of 4, this would be a40. The other two terms will not be contributing. Then you have to the power of 2. Okay, so this would be, first term will not make any contribution over here, second term will make. So, and the fourth term will also not make, so let's take this one at a time. So a22 x square y square, first differentiate it with respect to x, so that would be making it 4 times 4 times of A22 plus A04. Okay, or let me just do this once. The thing about stress functions is, Airy's stress function is that they are lengthier to do, easy but lengthier to solve. So let's take it one step at a time. Okay. So if you differentiate the first term with respect to x4, we get 4 into 3 into 2 into 1, A40. The second and the third term would give you 0, so I am not writing that. Now take this, differentiate the first term will be 0, second term would give you 2 into 1 into 2 into 1. Okay, A22 plus 0 plus again 4, so 0 plus 0 plus 4 into 3 into 2 into 1. Okay, this implies that the left hand side is actually equal to 8 into 3 A40 plus 8 into A22 plus 8 into 3 what is this from A04. 04. Okay, and if you take 8 outside, you will have 3A40 plus A22 plus 3A04. Now the left hand side is equal to 0 only when 3A40 plus A22 plus 3A04 is equal to 0. Okay, if it is not equal to 0, then this left hand side will not be equal to 0, and hence it will not satisfy the Airy stress function. So this is the meaning of the fact that for m plus n greater than 0, m plus n greater than 3, amn must be related. Okay, in this case they are related by this, in some other situation it's been related by some other function. So there is one constant in terms of the other two, and thus the two constants to be determined. So in this case, for example, you have to determine any two constants, because the third one you can find using this relation. Okay. If you now substitute the series into the biharmonic equation, okay, this infinite series which you have, so put phi x y, this was something which you had assumed. If you assume it to be of some other form, then there are other ways to solve it. So this is just to discuss where a polynomial Airy stress function can be assumed. In this implies? Let's see. M is equal to 4. Amn x my n minus 4 is equal to 0. You should verify this. It is easy to verify. Just put this into this and then write it of this form. So this is clearly the first term, this is the second term, and this is the third term. And this should give you an idea how many times. So clearly this has been differentiated 4 times, and that's why this is occurring like this. Okay. So please verify this. Now what we want to do is you collect the powers of x and y together. Okay. Meaning put m equal to 2 and n equal to 2. This is also something which you should verify. Don't leave it. Don't do this mistake that it's too simple, I'll be able to do. But because when the time strikes, it's very hard to do if you have not done all this before. Okay. So please do this. Collect the powers of this together. And very carefully you have seen how it has written. Now, if this equation has to be satisfied for all x comma y, everything in this bracket basically has to be equal to 0. So this would mean that m plus 2, m plus 1, m minus 1, a m plus 2, n minus 2 plus 2m m minus 1, n minus 1, a m n plus n plus 2 . Okay, so this is the relationship which all the coefficients should have with each other. Okay, so this, so that the biharmonic equation is satisfied. So this is the general form of the equation. And you have seen how this method can now be used, because if you assume it of this form, you have the constants, and then you sort of find the stress fields internal. Okay. So one of the things is that because you have taken your phi to be a polynomial, the stress may also turn out to be of a certain form, and hence it may not satisfy just about any boundary condition. How do you get around this problem? Using Saint Venant's principle. You slightly modify the boundary conditions, okay, so that it fits your taking phi as a polynomial. And once you do that, you should be able to use the Saint Venant's principle and say, well, we are only concerned with points which are away from the boundary, and hence the solution must approximately be the same for this. Okay, so there is an example in your textbook which you should check on your own. Okay, so that's a uniaxial tension. And we will be using this stress function in the rest of this course, so please understand until here very carefully. It will only get more complicated from here, so you should understand the basic philosophy about phi. Okay, that's what we will do. Many times we'll be using polynomial or some other form, but this idea remains the same. Okay, so we'll be discussing the in future how to be used in problems of elasticity. Thank you.